Listen up, everyone. Welcome to this explainer. If you're watching this, you're gearing up for some of the most brutal engineering entrance exams on the planet. I'm putting on my coach's hat right now because, frankly, we need a serious reality check. Too many of you treat kinematics like it's just some basic warm-up before the real physics starts. You memorize a couple of formulas, skim the chapter, and think, yeah, I got this. But here's the tough love. Your fundamental misunderstanding of kinematics is the exact thing quietly sabotaging your scores in advanced mechanics, electromagnetism, and even thermodynamics. Today, we're putting a stop to that.
Let's be real for a second. How many of you look at the syllabus and think, kinematics? Ah, yeah, easy chapter, guaranteed marks. Well, I'm here to bust that myth wide open. An easy concept is only actually easy if you get it right when the clock is ticking. If you jump into an allegedly simple question, rush it, make a dumb mistake, and lose those points, or worse, get slapped with negative marks, then guess what? That topic wasn't easy for you at all. It was a trap. We've got to rethink your whole exam strategy, and it starts right here at the foundation.
I want you to look at this number and burn it into your brain. 2.42. That is the harsh reality of your exam. When you take the total time allotted and subtract all the administrative nonsense, you are left with roughly 2.42 minutes per question. That's literally it. The stakes are incredibly high. If you're fumbling with basic kinematic concepts halfway through the paper, you are bleeding time you absolutely do not have. Mastering this stuff isn't just about getting the right answer, it's about getting it so fast and so efficiently that you steal back precious seconds to use on the absolute nightmares later in the test.
Okay, let's dive into this. Here is your strategic playbook for today. 1. The exam myth. 2. Reference frames and observers. 3. Distance versus displacement traps. 4. The velocity physics web. And 5. Mastering acceleration and time. Section 1. The exam myth. Accuracy over arrogance.
An easy topic is only easy if you actually get the answers right and secure the reward. That pretty much sums up what we were just talking about. The examiners know you've studied this material, so what's their game? They aren't just testing if you know the formulas, they are testing your accuracy under intense pressure. They actively design scenarios where overconfidence leads to careless errors. Your one and only goal in kinematics is machine-like accuracy. Execute the problem perfectly, pocket the reward, and move on.
Moving on to Section 2. Reference frames and observers, the foundation of motion.
Okay, so motion is a combined property of the object and the observer. You literally cannot say if something is moving unless you first establish who is looking at it. Think of it like this. You and I are sitting in a room right now. To each other, we're completely still, right? But to an observer chilling on the moon with a telescope, we are rocketing through space as the Earth spins and orbits the sun. Motion doesn't just exist out there on its own. It only exists relative to a specific observer.
And how does this connect to the heavy-hitting topics? We'll take center of mass. We've all seen that classic problem. Two people are sitting on a floating boat on a perfectly calm lake. One person walks toward the other, and you have to find the displacement of the boat. What's the usual knee-jerk reaction? You dive straight into writing out position vectors and mass equations. And look, I gotta playfully scold you a bit here. What are you doing? How on earth can you write a position vector without defining your origin? The origin is your observer. If you don't declare, okay, the center of the boat is my origin right at the start, your entire math equation is just floating in the void. It's a foundational kinematics rule that everyone just suddenly abandons when they hit center of mass. Don't lose your basics.
That brings us to Section 3, Distance versus Displacement Traps, Navigating the Minefield.
To permanently separate these two concepts in your head, I want you to think of distance as the actual fuel burned in your scooter. You could drive around your neighborhood in loops for hours, park back in your exact same driveway, but you still burned gas, right? Distance is the grueling, sweaty journey you actually took. Displacement, on the other hand, that's like your nosy relatives asking about your exam results. They don't care about your late-night study sessions, the stress, or the effort. They care about one thing, the final result. The shortest, straightest line from where you started to where you finished. So remember, distance is the scooter fuel, displacement is the nosy relative.
Let's look at how test setters weaponize this against you. Trap number 1, simple harmonic motion. Step 1, a particle starts at the mean position, x equals 0, swings out to the extreme positive a, and then swings all the way back through 0 to negative a. Step 2, the exam explicitly asks for the total distance traveled, but you're stressed, the clock is ticking, and your brain is hardwired to just plug time into the SHM equation. And what does that equation give you? Position, which means displacement, so you blindly write down negative a as your answer and lose the points.
The actual distance? It went a to the right, then 2a the swing all the way across to the left, making the total distance 3a. You completely knew the physics, but you tripped over the oldest vocabulary trick in the book.
Oh, and here's another classic, the circular motion trap. They ask you for the distance and displacement between 2 points on a circle separated by an angle theta. Now, total distance is just the arc length, r times theta. Very straightforward. But for displacement, you need that shortest straight line between the 2 points. In the absolute panic of the exam, while doing vector subtraction, so many students accidentally write down 2r cosine theta over 2 instead of the correct 2r sine theta over 2. And let me tell you, the exam setters are praying you make that tiny little trig mix-up. In fact, I guarantee 2r cosine theta over 2 will be option A on the multiple choice, just sitting there waiting for you to confidently select it. Slow down, differentiate between your path length and your straight line, draw your vectors, and get it right.
Section 4. The Velocity Physics Web. Everything is connected.
Let's see how this builds and branches out across your entire syllabus. You really think displacement and velocity just stay quarantined in Chapter 1? Not a chance. In work, power, energy, finding work means you're taking the dot product of force and displacement vectors. Center of mass, like we just said, you're totally lost without defining an origin to track displacement. Simple harmonic motion relies entirely on determining that mean position. And what if we jump all the way to grade 12 magnetism? The magnetic force equation, F equals QV cross B, absolutely demands that you know the exact direction of the velocity vector. If your vector kinematics are shaky, it's going to tank your magnetism scores too.
It goes even deeper. Here are a few rapid-fire places where velocity is hiding in plain sight. Power calculations? Power is literally the dot product of force and velocity. Kinetic theory of gases and thermodynamics? The whole concept of pressure comes from particles bouncing off walls, which relies heavily on root mean square speed and average speed. Electromagnetic induction? Motional EMF is calculated using B, L, and V. Yep, velocity. Velocity is not just about cars driving down a straight road, it is the master key that unlocks thermal physics and electromagnetism too.
Finally, Section 5, Mastering Acceleration and Time, Avoiding the Bad Company Trap. Here's a question for you. Does a negative acceleration always mean an object is slowing down? I hear this constantly. Oh, the acceleration's negative, so it's retardation. The object is hitting the brakes. Absolutely wrong. And this assumption is the exact trap that snags even top-tier students when they hit vertical motion or relative velocity questions.
Let's break this down. If velocity is positive and acceleration is positive, you speed up. If velocity is positive and acceleration is negative, you slow down. Simple, right? But here's the trap. If velocity is negative and acceleration is also negative, you actually speed up. And this brilliantly illustrates what I call the bad company analogy. Imagine a kid with a deeply negative attitude. If he starts hanging around a group of friends who are also wildly negative, that group is the acceleration, does that kid slow down his bad behavior? Obviously not. His negativity speeds up in the wrong direction. Acceleration sign simply tells you which way it's pushing. If it pushes in the exact same direction you are already moving, your speed increases, period. It doesn't matter if that direction is mathematically defined as positive or negative.
Let's connect this to those calculus graph questions that always seem to pop up. Looking at a position time graph, the slope of a secant line, which is just a line connecting two separate points, gives you the average velocity over that specific duration of time. But if you take those 2 points and you squeeze them together, shrinking that time interval closer and closer until the duration is practically zero, that secant line transforms into a tangent line, touching just one single point. The slope of that tangent represents your instantaneous values. It's the difference between calculating your average speed over a 5-hour road trip versus checking exactly what your car's speedometer says at one specific frozen millisecond in time. Squeezing the secant interval down to zero gives you the tangent. That's not just abstract math, that's the physical reality of differentiation.
And speaking of cars, we have to talk about one last trap before we wrap up, the reaction time trap. You know the problem. A driver sees a puppy in the road and slams on the brakes. The problem gives you the deceleration and asks for the total stopping distance. What do most people do? They plug the initial velocity and deceleration straight into the formula. But they completely ignore reaction time. While that driver's brain is processing the puppy and their foot is physically moving to the brake pedal, which maybe takes half a second, the car is still barreling forward at its original constant velocity. You absolutely must calculate that initial constant velocity distance first and then add the braking deceleration distance to it. Those split seconds matter both for the puppy and for your exam score.
So I'll leave you with this final provocative thought. If kinematics is truly the master key, the absolute foundational operating system that unlocks and dictates your success in every advanced chapter from thermodynamics to magnetism to simple harmonic motion. Are you finally going to give it the respect it actually deserves? Stop treating it like a trivial warm-up. Go back to your basics, define your origins, respect the difference between distance and displacement. Once you do, watch how it magically buys you back those precious, valuable minutes in your 2.42-minute exam window. Keep learning, keep pushing yourselves, and I'll see you in the next explainer.